The following program is brought to you by Caltech.
Our next speaker is going to bring us back very close to home. Our next speaker is John Johnson, who's an assistant professor of planetary science and astronomy here at Caltech. Richard showed you the Blue Book, which was written in 1985. One of the interesting things about the Blue Book is that there was no discussion about studying planets orbiting other stars. They didn't exist. John has been one of the leaders in developing this blossoming field that really only began in the mid-90s. And he's and the Keck Observatory, the Keck telescopes, have been a major force in studying planets orbiting other stars. And John will tell us about what he's up to with that. Thank you, John.
Thank you very much. So I'm going to be talking to you about exoplanets, which are planets that orbit other stars. We now live in an era where we know of thousands of these planets orbiting other stars in our own galaxy. Most of these are in our immediate solar neighborhood. And a lot of the work that I'm going to be showing, well, actually all of the work I'm going to be showing you today is based on data that are coming from NASA's highly successful Kepler mission. And even though this is a very successful space mission, it is through the support of ground-based observations that we've been able to help the Kepler team and their data reach its full potential in teaching us about planets around other stars. So this is the Kepler Space Telescope. It is a beautiful instrument. It's beautiful for its simplicity. It is a 1-meter Schmidt telescope in space. It was launched back in 2009. It's in an Earth-trailing orbit. It's getting further away from the Earth as time goes on. And once it reached its orbital point, it blew off a dust cover off the front end there. And now it has no more moving parts. Well, actually it has some reaction wheels. But it stares at one particular part of the galaxy, unflinchingly. And it has been measuring the brightnesses of about 150,000 stars in this region of the galaxy just off of the constellation Cygnus, and has been doing so for the past 3.5 years. There are no filter wheels, there are no instruments to swap out, there is just a primary mirror and a focal plane lined with silicon designed for measuring the brightnesses of stars. Now why? Why does it do that? Well, what we're looking for are the periodic diminutions in starlight caused when a planet eclipses its star. And so what we measure is, in time, we measure the brightness of the star, and occasionally we see a dip. And the depth of that transit event gives you the ratio of the areas of this planet to the star. And so what you get is the ratio, the planet's radius over the star's radius. And because we know the exact inclination of the orbit, which you don't get with some other techniques, we can actually follow up using something like the Keck telescope and measure the mass of the planet. And with both the mass and the radius of a planet, now you have some information about its bulk composition because you have its density. Now, this is the discovery technique. If it were this simple, it would be nice, but of course there's complications. And so what I'm going to be taking you through are the tools that we've been using to understand these planets, both to characterize them, but the first step is actually to validate that they're real. So what the data look like when they come down is that you might see the time series of photometric measurements, and you see this nice dip. Whew, you have yourself a candidate. And the Kepler team is extraordinarily careful about what they call these things. They call them Kepler object of interest. All right? So it's a little less sexy than saying we found a new planet. Now, we found an object of interest. And so once we have a dip, we have identified what we think is a star with a planet, or what we hope, but what we need to do now is validate it. And this is the work being done by a student here at Caltech named Tim Morton. And this is a primary part of his thesis work. And what we do is we try to assess the probability that this is an actual planet. Now, why do we go through this big exercise? Well, we hope it's this situation, planet passing in front of the star. You can have situations where you misclassify the star, and actually what you have is another very low mass star passing in front of a large star. It turns out that this doesn't happen too frequently. The thing that really jumps up and bites us most frequently is that Kepler has big chunky pixels. It has very bad spatial resolution. This is the irony of it. It's in space where you expect to have really beautiful angular resolution, but instead its pixel might be the size of this entire screen, and here's the star that you think is just one star, but right next to it is another star and another star. And so this little star eclipses the medium-sized star and blocks about 10% of its light. But this thing only contributes about 10% of all of the light in this entire 3-star system, making it look like a 1% transit event. And so this is a false positive probability you look at and you say, come on, John, how frequently does that happen? Well, this is the most common type of false positive event, and the galaxy is really clever at putting these things together along our line of sight. And what we need is a means of ferreting these things out and separating them from the genuine planet signals. And there's also this configuration where you have 2 big stars and there's a grazing configuration. But it turns out that you can, by eye, you can rule those out. So again, I just want to focus your attention back to this triple star scenario. And the way that we figure this out is that Tim has constructed on his computer a model of the stellar population of our galaxy along the line of sight from the Earth to the Kepler field, which is this one field in the entire galaxy. And he populates this with all of the stars using various models of stellar birth and death. And then he just assesses for each target where we have an object of interest, what is the likelihood that we are seeing 3 stars lined up versus we're seeing 1 star with a planet. And so using the statistical validation technique, we can then start separating candidates or graduating candidates into full-fledged planethood. One of the things that really helps is that to get much finer angular resolution on the sky. So if there is a star next to what we think is the target star that's actually responsible for the transit event, if we can use the Keck telescopes to separate its light out from, separate the light from those various stars, and then we can tell that we're seeing a potential false positive. And with the tremendously large aperture of the Keck telescopes, we get amazingly good spatial resolution. This is work done by a former postdoc and now professor at Notre Dame, Justin Krepp, and others. And so what I'm going to do in the next few slides is take you through examples of some of the things that we found. And this particular one started off, well, as a real planet candidate, and then it turned into a false positive, and then it was very disappointing, and then it turned into something extremely interesting. So here is the transit signal that we saw from the Kepler telescope, basically just beads on a stream, perfect photometric precision, and this is a very deep transit event. The particular star that we were looking at is called LHS 6343. It might be your favorite star too. And it is a red dwarf star, much smaller than the sun. And the depth of this transit indicated that it might be a Neptune-sized planet orbiting or transiting an M-dwarf. And at the time, there was only one Neptune-sized planet known to transit an M-dwarf. And for various reasons, that was extraordinarily interesting. So we thought this would be a great target to cut our teeth on. And just to compare, this is a ground-based transit-like curve from a 1-meter telescope, about the same size as Kepler. And this is just the effect of the Earth's atmosphere versus being out in space. All right, so what we needed to do is to figure out what we were looking at. All right, so Kepler thought it was just 1 star. We used adaptive optics, and it turned out to be 2 stars. So I could actually remember the disappointment that I felt that night looking at the quick readout screen that showed 2 stars sitting here, and I looked over at Justin and I said, well, geez, I guess this is gonna be a lot harder than we thought. So we thought we had a false positive. Now, little did I remember that I had scheduled observations on the high-res spectrometer at Keck for the next night, and then a couple of nights thereafter. If I had remembered, I would have canceled them, and I would have used the pressure Keck high-res time for something else. Fortunately, I forgot, because we got spectra of the stars, and we were able to see that star A, the brighter star, had changed its velocity by kilometers per second. It was accelerating, which means that something very massive was tugging on it. And the mass of the thing that was tugging on it was not consistent, and the period was completely inconsistent with that neighboring star. And the nature of the variations just didn't fit in with a star eclipsing a star. So what we thought was a false positive probability turned into a mystery worth looking into a bit more. So we got more measurements, and we were able to measure the velocity of the star in time and see exactly how it was accelerating. And when we were done, we had the mass and the radius of an object that put it squarely in this unpopulated region of the mass radius diagram for objects that you find out in space. This particular thing was much more massive than Jupiter. This is about 60 Jupiter masses, but it was only about 80% the radius of Jupiter. So you had 60 times the mass of Jupiter crammed into a volume that was significantly smaller. And that type of object is known as a brown dwarf. It was a failed star that was transiting one of those two M dwarfs. So we actually were seeing 3 objects. It's just that third object was way more interesting than we gave it credit for in the beginning. And at the time that we made this measurement, it was the only object in between here and here. And you notice that as you pile more and more mass onto these things, they actually get smaller. And this is due to an exotic type of pressure known as electron degeneracy pressure. And it just has this weird feature where the objects get smaller the more massive they are. And this was one of the first validations of this effect within the interior structures of brown dwarfs. The next object is Kepler object of interest number 254. It's another red dwarf star. And it had as transit, well, here's the overall Kepler light curve as we saw it. It had these huge sinusoidal oscillations, which we now interpret as star spot groups moving across the face of the star. And that allowed us to measure the rotation period of the star, which is useful for determining its age. And then you can see this kind of fuzz down below. And these are the individual transit events that happen on much shorter timescales than spots rotating across the surface. These happen over hour timescales. And so when you take this whole light curve and you fold it over itself and you can see the overall signal, you get this thing here. This is the Kepler light curve. And again, for comparison, this is observing that same star from the ground with the same size telescope, much worse precision. And so this indicated that we were seeing a Jupiter-sized object around an M-type star. Now, statistical validation was a little bit difficult for this one because you'd like to assess the probability of a false positive against the probability that it's a planet. And the probability that it's a planet was extraordinarily small because no hot Jupiter, no Jupiter-sized planet in a few-day orbit had ever been observed around a red dwarf star before. So that made that comparison very difficult to do. We'd never seen one before, so how do you make that assessment? So what we needed to do was have another means of confirming the planet nature of this object. And so what we turned to again was Keck high-res to make radial velocity measurements. This object is 60 times less massive, actually 120 times less massive than that other one that I showed you. And it therefore tugs on its star with a much weaker force of gravity, causing it to move by only about 70 meters per second instead of the kilometers per second that I showed you before. And this may not look like very impressive radial velocity precision if you've ever seen RV plots for the planets that we found before. But when you take into account the fact that this thing is about 100,000 times fainter than our typical star, you can start to see the power of the Keck telescope. This allowed us to dynamically confirm the first hot Jupiter that had ever been discovered around a red dwarf star. And this gives us important clues about how Jupiter-mass planets form. The next object of interest is KOI 961. And this is another interesting story where it was misidentified in the Kepler catalog as a much larger star. Therefore, its planets looked much larger. And the story that was told to us by the Kepler team for this particular object, it was a very short story, but it was very interesting, is that they thought they had 3 Jupiter-sized planets orbiting within 2 days of the star. And you don't need to have a degree in orbital dynamics to understand that that's a very unstable situation. Those planets are going to feel each other's gravity, it's going to toss them all around, it should go unstable in a few orbits. And so looking at it, we thought this has to be a false positive unless they mischaracterize the star. And so we used the high-res spectrometer and a number of other instruments, and we actually recharacterized the star. And when we were done, we revised the sizes of those planets down significantly. Here they are, the 3 planets, all with periods less than 2 days compared to our Earth and Mars. So these were some of the first sub-Earth-sized planets that had ever been detected. And they held the record for about a year up until a few weeks ago. There is now a moon-sized planet over here that Kepler has discovered. None of these are habitable, but they are unambiguously rocky in nature and some of the smallest planets that we know of outside of our solar system. And the architecture of the system is also very interesting. All of these planets orbit within 2 days of their star. And to do the press release, we wanted to put it have a comparison with other known planetary systems. So we thought, oh, let's pick the first hot Jupiter system, 51 Peg B, from back in 1995. And you put that on here, and the star is this big, and the planet, even though it's really close, is be over on that wall over there. So it didn't really fit for scale. So the best comparison we found was Jupiter and the 4 Galilean moons, shown here for comparison against this microplanetary system. So this is interesting for a number of reasons. Some of the smallest planets have been discovered, the smallest host star, which is not much bigger than Jupiter, and the overall compact nature of the orbital system is all very unusual, but, well, at least until we discovered it. And statistical analysis of these types of systems found by Kepler indicates this might be one of the most common types of solar systems throughout the galaxy. So the last one I want to show you is Kepler Object of Interest 952, which has since been renamed to Kepler 32. This is work done by John Swift, a postdoc here. The previous one was by Phil Muirhead, another postdoc here at Caltech. And this final system I want to show you is, I think, very representative of the final outcome of planet formation throughout the galaxy. And here is the family portrait of this system. Again, a red dwarf star in the center, a sub-Earth-sized planet in a 0.7-day orbit. You know, so you don't want to have to pay taxes on this particular planet. Then you have 3 kind of super-Earth, sub-Neptune-sized objects out here that have a really weird configuration. Well, not weird, but very particular orbital architecture of 1 to 2 to 3 period commensurability in here, which tells us something very important about how this planet formed. And this outer planet actually resides within the so-called habitable zone of this star, even though it has a period of only 22 days. And it's just because that star is so faint and so cool that the warm, temperate region around it is pushed in really close to the star, which is one of the advantages of looking at these red dwarfs. Now, the planet is most certainly not habitable. It's a big, puffy, kind of Neptune-sized object. But it just shows the promise of studying these small stars using the Kepler Space Telescope. And this right here, we believe, is a very typical outcome of planet formation throughout the galaxy. These are 5 planets all orbiting within the Mercury-Sun distance within our own solar system. And through a detailed analysis that we made as part of the study of this system, we found that there are about 1 to 1.5 small planets per red dwarf throughout the galaxy. And as Evan showed us before, there's about 50 billion stars throughout the galaxy. Most of them are red dwarfs. So that indicates that there's something like, I don't know, a order of magnitude 100 billion Earth-sized planets throughout the galaxy. And we know that that's a new result to science as of this year, thanks in large part to the Kepler Space Telescope and follow-up work on the ground using the mighty Keck telescopes. And so here's a quick summary of what we've been up to. We've been characterizing these cool Kepler objects of interest by characterizing the star and distinguishing them from false positives. Stellar astrophysics has really been key, as well as ground-based spectroscopy with the Keck telescopes. We validated and characterized some of the smallest planets that have been known. We also have some of the biggest planets that have ever been discovered around red dwarf stars. Even these false positives have turned out to be interesting. And so we've uncovered clues about the dominant mode of planet formation throughout the galaxy. When I used to give these types of talks, one of the common questions I would get after is, so what are we learning about our solar system? And I used to answer, well, we have to wait a long time before we can find true Jupiter-sized planets because they take 12 years to go around their stars, and Earths are hard to find. Well, actually, we have an answer to that now. It looks like the most common type of planetary system is around a red dwarf in the galaxy with a bunch of small planets inside the orbit of Mercury. And our solar system is just starting to look weird by virtue of having a yellow star and basically a completely empty region in close to it. And so we're getting a really grand galactic context for our own solar system by studying these planets around other stars. So this work has been done with the Keck telescope. It's also been done by the extraordinarily productive group of students and postdocs that I have with me here at Caltech. Thanks to the work that we've been doing at Keck, we've published about 20 papers based on Kepler data in the past 2 years, and our rate is only increasing. And so I'd like to just thank the people in the group and my collaborators, and I thank you.